Apart from this option 1 and 2, there is another option also sometimes required to use, which you can say is more effective compared to option 1 and 2, that you can say. Here what we used to do, here generally instead of what it is cooling to preheat temperature, here generally we cool the what it is called welded specimen to a temperature which is below martensitic 90% temperature range, we cool it down. Then what happens, whatever the untransferred austenite were there, that untransferred austenite also will be converted to martensite. Then generally from this below M90 degree centigrade temperature, generally we heat it. After heating, generally what happens, once we heat it, this heating temperature can be followed option 1 or option 2. Generally here we use option 2, generally after martensitic 90% transformation range, we heat the welded specimen to a temperature around 600 to 750 degree centigrade temperature, and we hold that position for a time of around what it is called 2 to 4 hours. After that, generally we cool down to room temperature slowly and steadily. What I am telling, understand, this is called option 3. So, what generally we used to do, graphically here I am showing. So, let us consider this is our preheat temperature TPH, this is our room temperature TR I am writing. So, this is room temperature, this is preheating temperature. So, what happens, we start the welding from preheating temperature, then we heat the specimen, then it is cooled down to preheat temperature. So, what happens here, instead of holding the cooling till preheat temperature, here we further cool down. This further cool down temperature is generally, this is your martensitic 90% transformation line, okay, or martensitic 90% temperature, okay. Let us say Tm I am writing, Tm90, okay. This Tm90, so below this Tm90 generally we reduce the temperature. After that, generally we preheat the welded specimen, preheat the welded specimen to a temperature of, either we can follow here option 1, option 1 means it can go to up to only preheating temperature range, or we can have a temperature of around 600 degree centigrade to 750 degree centigrade temperature depending on type of steel, and it is generally below recrystallization temperature. This you should keep it in mind. And after that, here we hold that temperature for a particular times. After that, we cool down this welded specimen to room temperature gradually. What I am telling, understand? This is called generally option 3. By this option also we can reduce the, what it is called, we can reduce the you can say chances of hydrogen induced cracking drastically. This you should keep it in mind. So, this types of heat treatment also preferable in case of also ferritic types of steel. And what happens? So, due to this heat treatment process, what are the things happen? There is a chance of formation of martensite till preheating temperature, and whatever the untransformed untransformed austenite were there, that austenite on it cool down below martensitic 90% transformation temperature range, then that untransformed austenite will be converted to martensite. So, what happens, whatever the overall martensitic transformation will be there. So, that overall martensite now we are tempering at a temperature of about preheating temperature or 600 to 750 degree centigrade temperature range. Then that martensite generally it is tempered below whatever the martensitic 90% temperature range is there, below that whatever the total martensite are there, both the martensite will be tempered, and what happens due to this temperament, it is converted to ferrite and carbide structure. So, here generally the final structure due to this heat treatment process will be ferrite plus carbide structure. Now, we will discuss about stress relief heat treatment operation. Stress relief heat treatment operation, you can see it has, you can say, one of the most important application to relieve the residual stress induced in welding specimen. This stress relief heat treatment generally we can define as the uniform heating of a structure, welded structure to a suitable temperature and holding at this temperature for a predetermined period of time, and after that we follow the uniform cooling. So, what is the definition of stress relief? So, stress relief treatment is defined as the uniform heating of a structure to a suitable temperature, holding at this temperature for a predetermined period of time, and finally followed by uniform cooling. Okay. Generally, this stress relief treatment usually performed, here also it is performed below critical range, what I am telling, understand. So, as not to affect the metallurgical structure of the workpiece, this you should keep it in mind. So, this stress relief operation also we carried out below, you can say, lower critical temperature, like in mass, that means below recrystallization temperature. So, that here metallurgical structural structure should not be affected. Here some curve here I am showing, here you can observe, higher the temperature you can see, generally higher is a you can say relief of initial stress. Here you can see, like what does this curve represent, like here this first curve, this top curve represent for holding time or soaking time is 1 hour, this second curve represent holding time for 2 hour and this 4 hour, and this third curve represent holding time for, you can say, 6 hour. So, for a particular temperature, if the temperature range here, let us consider for 430 degree centigrade temperature, if your holding time, that means here you can say initial temperature relief, that means it is remove, relief means really removal of initial stress, that means removal of residual stress. That means for a 430 degree centigrade temperature, for if we hold time is 6 hour, then you can say, here you can see your around 55% stress relief is done. Stress relief is done means 55% residual stress is removed, that you can say. If you hold this 430 degree centigrade temperature for 4 hour, then you can see here the release or you can say removal of this residual stress is around, you can say, for 47%. Okay. If the time is further less, then also you can say your residual stress relief also further decrease. That means what happens, your residual stress relief is around 40%. So, what we can observe, for a particular temperature, if your soaking time is, you can say, increase, or percentage of reduction of residual stress increase, this you should keep it in mind. Further, for a particular holding time or soaking time, if we increase the temperature, like let us 705 degree centigrade temperature, what you can observe, for 6 hour soaking time you can get around 100% residual stress relief, whereas for 705 degree centigrade for 4 hour soaking time you will get a percentage of relief of residual stress around, you can say, 98%, whereas if you further, if we reduce the time, then what happens, your residual stress, you can say, mitigation or residual stress reduction also will be decreased, what I am telling, understand. So, what we can observe from this curve, that means by using what is called by increasing the post heating temperature and holding time, we can relieve the residual stress from the weld specimen drastically, what I am telling, understand. For that both time and temperature have a effect. So, what we observe for a particular temperature, once we increase the time, then percentage of reduction of residual stress is increased. Then what happens, if we for a particular time, if we increase the temperature, then also percentage of reduction of residual stress will increase. This you should keep it in mind. Okay. Now, in this stress relief related things I will discuss little bit more detail. So, to reduce this high level of residual stress in weld specimen, the component is reheated to a sufficiently high temperature. What I have told you, this temperature though it is high, but it is below recrystallization temperature, this you should keep it in mind. So, at this temperature what happens, as the temperature is increased, the proof strength fall, which is allowing deformation to occurs and residual stress to decrease until an acceptable level is reached. This you should keep it in mind. This residual stress decrease generally we should consider for a acceptable level by holding the soaking time. This you should keep it in mind. Okay. The component would be held at this temperature, or this temperature means this soaking temperature, for a period of time until a stable condition is reached and then cool back to room temperature. The residual stress remaining in the joint is equal to the proof strength at this soak temperature, This you should keep it in mind. What does it means? I will explain in details, okay, here itself. So, residual stress in carbon manganese steel generally it falls reasonably steadily from ambient temperature to 600 degree centigrade temperature, but for high strength creep resistance steel, generally this residual stress start to fall from 400 degree centigrade temperature before the residual stress began to fall. What I am telling, understand? That means, in case of carbon manganese steel, the residual stress you can say start to fall from ambient temperature to 600 degree centigrade temperature, whereas for high strength creep resistance steel, it need a temperature to falling starting of this falling of residual stress, it need a initial temperature of 400 degree centigrade. This you should keep it in mind. So, there is therefore you can see a range of soaking temperature for various types of alloy are there to achieve an acceptable reduction in residual stress. And another things you should keep it in mind, this temperature which should not adversely affect the mechanical property of the joint. This you should also keep it in mind. That is why here I have written what should be the temperature range for stress relief operation. Like in case of carbon manganese steel, this temperature will be between 550 to 620 degree centigrade. In case of creep resistant steel, somewhere between 650 to 750 degree centigrade temperature, and for stainless steel this temperature between 800 to 850 degree centigrade temperature. So, here I have just discussed in details about stress relief post weld heat treatment. So, here I have discussed about a term that is called proof strength. Generally once the temperature increase, then proof strength fall. Proof strength, what is proof strength? You know very well. In case of some material, proof strength means we know, this is the stress strain curve of a material. Proof strength means for 0.2% strain level, this is your strain, this is your stress. If we draw a line which is parallel to initial tangent means initial tangent, if it is parallel to initial tangent, where its cut this stress strain curve, whatever the stress is there, this stress is called generally you can say sigma proof stress. That means at 0.2% strain level, if we draw a line which is parallel to the initial tangent of this stress strain curve, then this 0.2% line where it is cutting this what is called stress strain curve, that cutting point whatever the stress is there, that stress is called proof stress. So, in some material this is generally called 0.2% yield stress also. Okay. Now, this proof stress generally always you should keep it in mind, proof stress generally depends on temperature. So, let this is your temperature, this is your temperature and this is your let us sigma proof. So, one thing you can observe that with increase the temperature generally this proof stress decrease. So, what happens, what this stress relief operation tell, let us if we heat at a temperature of around 600 degree centigrade temperature, at this 600 temperature let us our proof stress is this mass, proof stress is this mass, let us it is 10% of actual residual stress, 10% of actual residual stress initially. So, at this temperature level, that means if we raise the Weldman's specimen at a temperature of this level, then whatever the proof stress will be there during this temperature level, that proof stress magnitude will be remain as a residual stress after this stress relief heat treatment operation. What I am telling, understand? This you should keep it in mind. Okay. Now, why this stress relief operation is required, little bit in details here I am discussing. Generally this stress relief operation is performed first of all we know that the high residual stress which is locked into a weld joint which may cause deformation outside acceptable dimension to occur when the item is machined or when it is enter in service. So, due to this thing generally what happens, stress relief operation is required to do to minimize this residual, because if this residual stress will be there, then once we machine that component or once we use this in a service condition, then due to this residual stress there can be occur some deformation which is outside the acceptable dimension, this you should keep it in mind. Apart from this thing, if there is a high residual stress in case of a weld specimen, that is carbon or low alloy steel types of weld specimen, then it increases the what is called risk of brittle fracture. So, if we do this stress relief operation, then what happens, this risk of brittle fracture we can eliminate. Apart from this thing, this tensile residual stress if we will remove, then what happens, it also reduce the cause of stress corrosion cracking. This is another phenomenon also you should keep it in mind. Generally if there is a high residual in a weld specimen, then there is a chance of stress corrosion cracking in the case of some what it is called some particular medium, like to occur this stress corrosion cracking high residual stress is required, as well as it is required for carbon and alloy is require caustic types of medium, and for stainless steel it requires generally chloride types of medium. If this medium is there, then due to this high residual stress there is a chance of stress corrosion cracking. So, once we mitigate or minimize this residual stress in the weld specimen, then there is a chance of less stress corrosion cracking also there in your weld specimen. Some other heat treatment process also we need to discuss. What are those other two heat treatment process? One is called annealing heat treatment process, another one is called normalizing, another one is called tempering, and another one is called aging or precipitation hardening operation, heat treatment operation. Little bit in the briefly I will discuss this heat treatment process also. Though you are very well familiar about all this heat treatment process, then also you should know little bit, because this is also sometime required in case of weld specimen. So, what is annealing operation? This annealing operation generally is a high temperature you can say heat treatment operation. This process require material heating generally above recrystallization temperature. You know, for mild steel recrystallization temperature is 723 degrees centigrade, it should be above that temperature, and we should hold this temperature for a particular time before cooling, then cooling slowly, and this process, generally this annealing process, we used to do these types of annealing operation in furnace. This is often carried out generally to soften the what is called hardened material. One thing you should keep it in mind, a fully annealed generally structure, you can say a fully annealed component giving the very softest of microstructure, this you should keep it in mind. It also result in reduction in both yield as well as tensile strength in case of ferritic types of steel, and also it is reduce the toughness also. Here one thing you should keep it in mind, in full annealing the carbon steel, here what we used to do, here we generally slowly heated a temperature of about 50 degree above the austenitic temperature, that means above austenitic temperature we further heated a temperature within a range of 50 degree centigrade, and after that we hold this temperature for a particular time, this is called, that is why it is called holding temperature, and then cooling down slowly to room temperature. Here one thing you should keep it in mind, in annealing operation the cooling rate is very slow. How it is, like what happens, this cooling rate is around 20 degrees centigrade per hour, that means per hour only 20 degrees centigrade temperature will be reduced, this you should keep it in mind. What is normalizing operation? This is also a heat treatment process which is carried out above recrystallization temperature, that means here the temperature is above the upper critical temperature, or you can say upper transformation temperature, and after within the temperature, upper transformation temperature, after that generally we hold this temperature for a particular times, after that we cooling it in still air, this you should keep it in, this normal air generally we cool it. Here this result in a generally reduction in grain size, and also it's improved the strength and toughness of the structure. So, this normalizing operation is a heat treatment that is also generally carried out in case of a ferritic types of steel, this you should keep it in mind. This normalizing operation generally it's reduce the grain size, that means is refine the grain size, as well as it's improve both strength and toughness. Another two heat treatment process I am going to discuss now, that is one is called tempering and another one is aging or precipitation hardening. So, what is tempering? Tempering is a heat treatment process which generally carried out in case of a ferritic types of steel at a relatively low temperature compared to, you can say, annealing or normalizing heat treatment operation. Here the temperature is below the, you can say, lower transformation temperature or lower critical temperature. In a conventional structure carbon steel, this would be within a range of around 600 to 650 degree centigrade temperature, this you should keep it in mind. Due to this tempering, generally here hardness is reduced, its tensile strength also reduced, but here due to this tempering operation it improves ductility and toughness. So, most normalized steel, one thing you should keep it in mind, whatever the steel which is normalized, that normalized steel generally required to tempered before welding. So, before welding operation, whatever the normalized steel are there, that you need to tempered, after that you should go for welding. Apart from this thing, whatever the quench steel is there, that quench steel also generally first quench, then tempering operation is required to do, after that generally we need to do the welding operation. This you should keep it in, that is why here I have written all quench steel are used in quench and tempered condition, this is also you should keep it in mind. Now, aging or precipitation hardening, this is also very important heat treatment operation. It is also a low temperature heat treatment operation which is designed to produce correct size and distribution of precipitates. What is precipitates? Precipitates generally is a, you can say, is a teeny, a small second phase element. What I am telling, understand? This element can be aluminum, copper, or it can be nitride types of structure, or carbide types of teeny particles generally are there. It is a second phase types of structure that you can say. So, by aging or precipitation hardening, what we used to do? We produce the correct size and distribution of these precipitates. Once we do these things, then what happens? It increase the yield and tensile strength. So, to increase the yield and tensile strength, this aging or precipitation hardening generally required to do. This aging hardening generally, you can say, preceded by a solution heat treatment. That means, it is a solution types of heat treatment process. For steel, this precipitation, or you can say this heat treatment temperature somewhere between 450 to 740 degree centigrade temperature, whereas for aluminum this temperature is varying within a range of 100 to 200 degree centigrade temperature. Here one thing you should keep it in mind, longer the time of this aging hardening, or you can say higher the temperature of this aging hardening, which results in an increase in size of the precipitates, and if the size of the precipitate increase, it generally reduce both hardness and strength. This you should keep it in mind. So, this all about different types of common heat treatment process which are used in welded specimen. In next lecture, I will discuss about what are the different types of heat source model generally we use for doing thermomechanical analysis. So, thank you.